In this video, we are going to look into nomenclature of alkenes and alkynes. Before we look at nomenclature itself, we should examine the concept of degree of unsaturation, or as it is also called, index of hydrogen deficiency. So, degree of unsaturation of an organic compound equals number of rings and number of pi or p orbitals. Now that's in theory. In practice, the way we calculate degree of unsaturation is by a formula of 2n plus 2, where n is number of carbon atoms. And note that 2n plus 2 is number of hydrogens in saturated carbon atom, minus m, divided by 2. So n is number of carbon atoms, and m is number of hydrogen and halogen atoms. Don't forget halogen, to include halogen atoms in this calculation. So here are some examples. This compound has 3 degrees of unsaturation. It has 2 fused rings and a double bond. Double bond is common to both rings, but it's 1 double bond and 2 rings. So that means 1 pi orbital and 2 rings, total of 3 degrees of unsaturation. This compound has 1 degree of unsaturation, 1 pi orbital. And this compound has 2 degrees of unsaturation, 1 ring and 1 pi orbital. So ordinary alkene with 1 pi bond would have 1 degree of unsaturation. Alkyne with 2 pi bonds, triple bond, that has 2 pi bonds, has 2 degrees of unsaturation. And ordinary cycloalkane, which has just 1 ring, would have 1 degree of unsaturation. Now we can look at nomenclature of alkenes and alkynes. We'll start with nomenclature of alkenes. So to name an alkene, we have to identify the longest chain that contains the double bond. Actually, it has to contain both carbons of the double bond. So that chain is the parent chain. Even if there is other longer chain in a molecule, if it doesn't contain both carbons of the double bond, it's not parent chain. It must contain both carbons of the double bond. Then we would first name it as alkane and then replace suffix a and e of the alkane with suffix "-ine" to indicate that it is an alkene. Then assign the first carbon of the double bond the lowest possible number. 2 carbons of the double bond should be assigned 2 consecutive numbers, and of course they should get the smallest possible numbers. We list only smaller of the 2 numbers and list that number, place it before the name of the parent chain. And then we name and number substituents. Substituents are listed in alphabetic order before the name of the parent chain. Here are some examples. First one, 7 carbons in a chain, we would name that as heptane. Since there is a double bond present, we replace a and e with e and e, so it's heptene. Double bond is given numbers 3 and 4. Those are smallest possible numbers. That means this is 3-heptene because we list only the smaller of the 2 numbers of the double bond. Since numbers have to be consecutive, we know that the other carbon of the double bond has to be carbon 4. So this is 3-heptene, and finally on carbon 6 there is chlorine atom, so 6-chloro 3-heptene. This one is a slightly more complex example because the longest chain has 9 carbon atoms. But this is not nonane or nonene because that longest chain does not contain double bond. You can see longest chain is indicated in red. It's indicated in red because it is not the parent chain. The parent chain, the longest chain that contains double bond, has only 8 carbons. So this is octane. And double bond is between carbons 2 and 3. So this is 2-octene. So octane, replace a and e with e and e, and indicate the double bond is between carbons 2 and 3. So 2-octene. Now on carbon 4, we have butane as substituent, and on carbon 7, methyl group, butyl group and methyl group. So name is going to be 4-butyl 7-methyl 2-octene. Certain groups that contain double bonds have their own names, and those are vinyl and allyl groups. Vinyl group is simplest double bond CH-CH2, so that's simply called vinyl group. Allyl group is double bond separated by one sp3 carbon atom from rest of the molecule. So its formula is CH2CH-CH2. These groups are used in trivial naming of various classes of compounds, or if they are substituents, then they are acceptable as names of the substituents. Here are some examples. This compound is vinyl bromide. It's also used in naming of ethers, so ethyl vinyl ether or amines. This is allyl amine, and this secondary amine contains both allyl and vinyl substituent, so it's called allyl vinyl amine. Here we have a little bit more complex example. Remember nomenclature of alcohols. Cyclopentanol has OH group on carbon 1, but we don't list carbon 1. We don't list it as number 1. We assume that it's understood that carbon with hydroxyl group is carbon 1. So substituents in this case are on carbons 2 and 3. On carbon 2 we have allyl group, 3 vinyl group. So this is 2 allyl, 3 vinyl cyclopentanol. We indicate or name carbon atoms as vinylic carbon atoms, or classify them, that's probably the best term. We classify carbon atoms as vinylic carbon atoms if they are carbon atoms of the double bond. So carbon atoms that are connected to each other by a double bond are vinylic carbon atoms. Carbon atoms next to vinylic carbon atoms are allylic carbon atoms. We also classify hydrogens the same way. Hydrogens attached to vinylic carbons are called vinylic hydrogens, and hydrogens attached to allylic carbons are called allylic hydrogens. Now we're going to look at nomenclature of cycloalkenes. So if the longest chain that contains a double bond is a ring, then the compound is named as a cycloalkene. Carbons of the double bond must be given numbers 1 and 2. Now that sounds obvious, but actually when there are substituents, it's very easy to make mistake of not assigning consecutive numbers to carbons of the double bond. So be very careful not to make that mistake. Unlike an open chain compound, where two carbons of the double bond obviously get consecutive numbers, and it's rather difficult not to give them consecutive numbers, in a ring we can start numbering at either of the two carbons of the double bond. We can go clockwise or counterclockwise, and it's very easy to make a mistake of not assigning them consecutive numbers. If cycloalkene contains only one double bond, then number 1 is not listed as part of the name. And so examples would be cyclobutene, cyclopentene, cyclodecene. So here we have cyclopentene, cyclodecene. So two formulas, and you can see we don't list number 1. We simply assume that double bond is 1, 2, and we actually don't specify which carbon is carbon 1, which is carbon 2. Either of the two could be 1 or 2. Then, if substituents are present, we name and number the substituents. Of course, keeping in mind that carbons of double bond have to be numbered 1 and 2. I keep emphasizing that. And then substituents are listed in alphabetic order before the name of the chain. If ring contains 2 or more double bonds, then all double bond numbers must be listed in the name. We'll cover that a little bit later. And now we are going to look at some examples of substitute cycloalkenes. First one is 1-chlorocyclopentene. So two carbons of the double bond are given numbers 1 and 2. And either carbon of the double bond could be carbon 1 or 2. But when substituent is present, then carbon that has substituent attached to it is carbon 1. So that's why this is 1-chlorocyclopentene. Next one is a little bit more complex example. That's 3-methylcyclobutene. A lot of students would have made a mistake here and named it 2-methylcyclobutene. That's why when naming cycloalkenes, it's a good idea to write down the numbers to make sure that carbons of the double bond are assigned consecutive numbers. 2-methylcyclobutene is non-existent compound, because if we assign number 1 to carbon atom of the double bond next to methyl group, and then 2 to methyl group, then double bond would end up with numbers 1, 4. And obviously that's against the nomenclature rules. Now, when we look at this compound, we can see which carbon is carbon 2, which carbon is double bond. If methyl group is attached to that carbon, then that becomes carbon 1, and then that would be methyl 1-cyclobutene. So for that reason, 2-methyl-cyclobutene does not exist. Here is another similar example for fluorocyclohexene. Again, be careful not to name this 3-fluorocyclohexene. Again, students will do that in attempt to assign substituent the smallest possible number. But 3-fluorocyclohexene, if you were to number it like that, then double carbons of the double bond would end up with numbers 1, 6. Again, non-consecutive numbers. And finally, this is another example where often students would make mistake. I have seen often students name this 3-chloro-2-methyl cyclopentene because that gives smaller set of numbers. Again, numbers 5 and 1 refer to substituents, and so 5 plus 1 is 6, while 2 plus 3 is 5, so smaller set. But if we were to name this 3-chloro-2-methyl cyclopentene, yes, that does give 1, 2 numbers to the double bond, and so double bond is numbered consecutively. So instead of numbering double bond 1, 2 counterclockwise, you would number double bond 1, 2 clockwise, and that gives number 2 to methyl group and 3 to chlorine or chloro substituent. But doing that means that we are assigning number 2 to carbon atom of the double bond that has substituent, and that's against nomenclature rules. So when double bond has only one substituent, we ignore all other substituents elsewhere in the molecule and assign number 1 to that carbon of the double bond. That, of course, automatically assigns number 2 to the other carbon of the double bond, and then rest of the ring is numbered accordingly. So correct name for this compound is 5-chloro-1-methyl-cyclopentene. Now we are going to look at nomenclature of alkynes. To name an alkyne, we identify the longest chain that contains the triple bond. Of course, it has to contain both carbons of the triple bond, but unlike alkenes, that's not a problem, because alkynes cannot branch. Alkenes can branch, alkynes cannot, so chain will always contain both carbons of the triple bond. So that chain is the parent chain. Next, we first name it as chain as alkane chain, and then to indicate that this is an alkyne, we replace ane suffix of alkane with yne suffix of alkyne. Then we assign smallest possible numbers to the 2 carbons of the triple bond, and the first carbon of the triple bond, of course, is given the lowest possible number, and then that number is placed before the name of the parent chain. Finally, we name and number the substituents, list substituents in alphabetic order, and place them before the name of the parent chain. So here we have one example. So you can see that actually longest chain has 7 carbons, but this is not, a parent chain is not heptane, because this is not an alkane, it's an alkyne. And longest chain that contains both carbons of the triple bond has 6 carbons. So as an alkyne, it would have been named as hexane. Now as an alkyne, it's named as hexyne. Carbons of the triple bond are carbons 1 and 2. We list only the smaller number, so this is 1 hexyne. And then on carbon 3, there is propyl substituent, so this is 3-propyl 1-hexyne. Alkynes are classified as terminal alkynes and internal alkynes. This is very important classification. It's used a lot in this course and organic chemistry in general, and you have to be familiar with it. Terminal alkyne has triple bond at the end of the carbon chain, while an internal alkyne has triple bond inside the carbon chain. As a consequence, 2 classes of alkynes have very different properties. So here are some examples of terminal alkynes, and you can see in each case triple bond is at the end of the chain, which means that each of the terminal alkynes has hydrogen atom attached to an sp3 hybridized carbon atom. And these are examples of internal alkynes. So in each case, triple bond is inside the chain. By the way, note the first example, cyclooctane. smallest ring that can contain triple bond is 8-membered ring. So this is the smallest cycloalkyne. And of course, you can see that internal alkynes do not have hydrogen attached to an sp hybridized carbon atom. That's a very important difference. Groups that contain triple bond are ethynyl and propargyl groups. So ethynyl group is simple triple bond. Ethynyl is CCH, and it's used in naming, trivial naming of certain compounds such as ethynyl bromide, or it could be used in naming substituents. Propargyl group is triple bond separated by one sp3 carbon atom from rest of the molecule, so CH2CCH. It could be used to name compounds such as propargyl bromide, propargyl alcohol. We have already covered groups that contain double bond, vinyl and allyl, so now you can see groups that contain triple bond. So ethynyl corresponds to vinyl, propargyl to allyl group. And here is how we use them in nomenclature. For example, as a substituent, this is ethynyl cyclopropane. And this would be propargyl cyclobutane. Here is one more complex example, naming of cycloalkene that has ethynyl and propargyl substituents. So this would be cyclopentene, and of course we have two carbons of double bond. One of them has substituent, so that's carbon 1. And that carbon 1 that has substituent has propargyl group as a substituent. And then the other carbon with substituent is carbon 3. That one has ethynyl group. So name of this compound is 3-ethynyl 1-propargyl cyclopentene. And so this completes our study of nomenclature of alkenes and alkynes. Next, we are going to look at isomerism of alkenes and nomenclature of dienes.